Welcome to the first lesson for Chem 345. As you might expect, in this first lesson we are going to be starting right at the beginning. To get us started learning about organic chemistry, we are going to need a good understanding of a few fundamental concepts to serve as a foundation for the subsequent lessons. These fundamental concepts, which include bonding, how acids and bases work, and how to depict and interpret structural formulas, are going to provide us with what we need to get started with this fascinating science. So with that being said, let's get started. Let's begin with a brief outline of topics that we will cover in Lesson 1. As you can see, Lesson 1 is broken down into 3 parts. In the first part of Lesson 1, we will start with a description of what organic chemistry is as a science, and introduce you to the goals of this science. After this introduction, you will begin learning some of the technical details of the language of organic chemistry. Specifically, you will be learning about the covalent bond, formal charge, Lewis structures, and resonance forms. There is a lot of information to grasp in this first part of the lesson, but once we have these tools at our disposal, we can move on to Part 2 and 3, where we will learn to confidently draw organic structures and depict how they change during chemical reactions. Organic chemistry, the branch of chemistry that explores the structure, properties, and reactions of organic compounds, is a fascinating field, with profound implications for our understanding of the natural world. Organic chemistry is the study of carbon-containing compounds, which form the basis of all living organisms and countless synthetic materials. From the DNA in our cells to the plastics in our everyday products, organic chemistry permeates every aspect of our lives. At its core, organic chemistry seeks to unravel the intricate dance of atoms and bonds that underlies the behavior of these compounds. By understanding how molecules interact and transform, scientists can design new drugs to combat disease, develop sustainable materials to reduce environmental impact, and uncover the secrets of biological processes. Organic chemistry isn't just a scientific discipline. It's a gateway to innovation, discovery, and progress. As we journey deeper into the realm of molecules, the possibilities are limitless. To understand the chemistry of carbon-based molecules, we need to first understand how carbon forms bonds to itself and other elements. Here we can see a picture of an abbreviated periodic table that shows the elements that are most important in organic compounds. We can see, for example, groups 1A through 8A are included here. These are also called the main group elements. The most important information that we will use from the periodic table, at least in the beginning, will be the group number. The group number is especially important to us because it specifies the number of valence electrons for elements within that group. As you may already know, it is through the valence electrons that chemical bonds are formed. Now, if you feel a little rusty on the concept of valence electrons, no need to worry. We are about to review the concept in some detail on the electronic structure of atoms. You probably remember from your previous chemistry courses that electrons are tiny, negatively charged particles that whirl around the nucleus of an atom in defined energy levels, or so-called shells. Valence electrons are the electrons found in the very outermost shell or energy level of an atom. The valence electrons are crucial because they determine the chemical properties and behavior of an atom. When chemists first organized elements into the periodic table, the placement of elements into groups was based on their physical and chemical properties. It was only later, after the discovery of the electron, that we learned that groups of elements also have the same number of valence electrons. You also probably remember learning that elements can gain, lose, or share these valence electrons to become more stable. As an example, you might recall that the most stable elements on the periodic table, the noble gases, are distinguished by their valence shell being completely full. In other words, they have a closed shell. The so-called octet rule derives from this observation. It provides us with a guideline that elements in the second row, the ones we are usually dealing with, will gain, lose, or share electrons in order to achieve 8 electrons in their valence shell. Let's take a closer look at why and how this happens on the next page. Understanding the octet rule and how electrons are arranged around atoms is helped by constructing electron configuration diagrams similar to the one shown below. These diagrams are a graphical summary showing the location of each electron around an atom. In this diagram we can see there are 3 regions, called shells, or principal energy levels, that are arranged from lower energy to higher energy. Within each of these shells we can see a number of platforms. These platforms represent the orbitals that exist within each energy level. When we populate the diagram with electrons, we are able to see which orbitals are filled, which are empty, and their relative energies. As a review, let's put together the electronic configuration for a carbon atom. We start by locating carbon on the periodic table, noting that it is in the second row. Because it is in row 2, a carbon atom will have 2 shells that contain orbitals. We can also see that carbon is in group 4, which means that a carbon atom will have 4 electrons in its valence shell. Let's start by drawing platforms for the orbitals in the lowest energy level, that is to say, the orbitals in the first shell. When the energy level is 1, as it is in the first shell, there is just one type of orbital. This orbital is described as the 1s orbital. The number 1 represents the energy level it is in, and s represents the type and shape of the orbital. Recall that s orbitals are spherically shaped. If you actually want to see a graphical depiction for the orbitals, there are several on the next page. Moving up in energy to the second shell, where n is equal to 2, we have 2 types of orbitals, the s orbital, and a different type called a p orbital. Recall that p orbitals are sometimes described as dumbbell-shaped. There is only one platform for the s orbital, which we designate as 2s, but there are 3 platforms for the 2 p orbitals. Notice that these p orbitals are at a higher energy within the shell, compared with the 2s orbital, but they all have the same energy as each other. This is called degeneracy. Each of the p orbitals is oriented along one of the Cartesian coordinates x, y, and z, and we typically refer to them as 2px, 2py, and 2pz respectively. Now that we have the orbitals mapped out, we can populate them with electrons. There are 2 guidelines we start with when filling the orbitals. First, each orbital can hold a maximum of 2 electrons. This is known as the Pauli exclusion principle. It states that electrons in the same orbital must have opposite spins. As electrons have only 2 spins, up and down, that means that orbitals max out with 2 electrons. The second guideline is that we will start by filling the lower energy levels first. This is called the Aufbau principle, which means building up. Always fill lower energy orbitals before higher orbitals are filled. Now that we have filled the first shell, it is time to move up into the second shell. The lowest energy orbital in this shell is the 2s orbital, which we can fill with 2 electrons. So far, we have used 4 electrons. A neutral carbon atom has 6 electrons, so that means we have 2 more to place on the diagram. Let's place one of these electrons in the first of the p orbitals. We now have 1 more to place. Do we place this electron in a different p orbital, or do we pair it up with the other electron? The principle we follow for this step is known as Hund's rule. Hund's rule says we should place 1 electron in each degenerate orbital before pairing them up with other electrons. Now if we take a look at what we have constructed here, we notice that the second shell, which is the valence shell for carbon, has 4 valence electrons. This matches what we predicted, using the group number from the periodic table. Note that 2 of the valence electrons are paired, and 2 are unpaired. We are going to see, in part 2 of this lesson, that this electron configuration diagram needs one additional layer in order to accurately describe bonding of carbon and other atoms in molecules. We are going to learn about a process known as orbital hybridization. Orbital hybridization will help us explain the shape and geometry of atoms within molecules, which in turn will help us understand and predict the three-dimensional nature of chemical reactions and how we can influence their outcome. Before we can get to those ideas, we need to cover a few more basics first. Let's go to the next page and look at a few graphical depictions of atomic orbitals, and then we can move on to the next part of this lesson, which covers the chemical bond. Here are a few graphical depictions of the s and p orbitals. Notice the spherical shape of the s orbitals, and that when a cutaway is made from the 2s orbital, we can see that it is superimposed on the smaller 1s orbital, like rings of an onion. We can visualize the nucleus of the atom at the center of these spheres, and the electrons whirling around outside of the nucleus within these orbitals. Now take a look at the shape of the 2p orbital. There are two lobes for each orbital, shaded differently in each to refer to the phase of the wave function for the orbital. These lobes do not represent distinct orbitals, but rather belong to the same orbital. Each lobe is separated by a node. Nodes are regions where there is zero electron density. The various p orbitals are superimposed around the nucleus of the atom, pointing in their respective directions in space. Let's review the concept of the chemical bond. As mentioned previously, many chemical reactions are defined by changes to the number of electrons in the valence shell. As elements seek to achieve a filled valence shell, they can form bonds with other atoms. As you have seen in your previous courses in chemistry, there are two fundamental types of bonds between atoms. The first type, called an ionic bond, results from the transfer of valence electrons either into the valence shell or out of the valence shell. This transfer of electrons causes the atom to become charged, either negatively charged or positively charged, depending on if it gained or lost electrons. These charged versions of atoms are called ions. The ionic bond is simply the electrostatic attraction between oppositely charged ions. The ions behave like small magnets and stick together with other, oppositely charged ions. The other type of bond is called a covalent bond. This type of bond does not involve the transfer, but rather the sharing of valence electrons between atoms. Carbon, for example, only has 4 valence electrons. Carbon therefore needs an additional 4 electrons to achieve an octet, and thus become more stable. If other nearby atoms, such as the 4 hydrogen atoms shown here, can share their electrons with carbon, carbon can achieve an octet. This sharing of electrons has brought the atoms within close proximity, and this is called covalent bonding. So, to recap, ionic bonding occurs when electrons are transferred from one atom to another, causing the atoms to become oppositely charged and stick together through electrostatic attraction. Covalent bonding, on the other hand, results when atoms share electrons with each other. Why do elements like carbon share electrons rather than transferring them? Unlike the alkali metals and the halogens, elements in the middle part of the periodic table require either losing or gaining multiple electrons in order to achieve a filled or closed shell of electrons. Carbon, for example, would need to transfer 4 electrons into or out of its valence shell if it were to achieve an octet by way of an ionic bond. Additionally, elements in the center of the main group are not at the extremes of electronegativity compared with alkali metals and the halogens, and so the transfer of electrons into and out of their shells is not as energetically beneficial. In your previous chemistry courses, you first learned how to draw molecules that contain covalent bonds by using Lewis dot structures. In these structures, you learned how to use dots around the 4 sides of the symbol for an element. These dots were used to keep track of bonding and non-bonding electrons in the valence shell of each atom within a compound. You learn to use lines to represent a covalent bond, which is just the sharing of two electrons between two atoms. Do you recall during our review of valence electrons that the number of bonds an atom will form depends on the number of valence electrons the atom needs to complete its octet? Excellent. What this means for us is that elements will always form a consistent number of bonds, and that we can figure this out ahead of time. Also, it means that atoms in the same group will form the same number of bonds as each other. This makes our job of drawing structures much easier. Let's look at carbon as an example. Because carbon needs 4 electrons to complete its valence shell, all of the carbon atoms in organic molecules will always have 4 bonds. In fact, the only time that we will see carbon without 4 bonds is when a molecule is undergoing a chemical reaction. During chemical reactions, we will often see that one or more covalent bonds is temporarily broken. In these instances, carbon and other atoms will be in a special, much more reactive state, simply because they are not in their most stable configuration. These special reactive states are very useful to us, because they allow us to cause molecules to react and undergo transformations with each other. During this course, you will be learning the techniques whereby we can put carbon and other atoms into these reactive states in order to cause chemical reactions. This will give you the knowledge and power that organic chemists use to design and construct new molecules. What bonding patterns do we see in other types of atoms, besides carbon? Let's look at the Lewis dot structures for some of the elements, and see if we can predict the number of bonds we expect for each. This will help us a lot when we learn to draw organic structures, because most of the really interesting organic compounds contain atoms like oxygen, nitrogen, halogens, and others. Since we are discussing covalent bonds rather than ionic, let's start with a nonmetal element such as boron in group 3. Because boron is in group 3, it has 3 valence electrons. We can depict these 3 valence electrons as unpaired dots around 3 of the 4 sides of the element symbol. The element aluminum, directly below boron, also has this same configuration. Because boron and aluminum have 3 unpaired electrons, these elements are frequently found in their neutral state with 3 covalent bonds. With only 3 bonds, however, these elements do not yet have an octet of electrons. They only have 6, and as a result, they are still quite reactive. To achieve an octet, boron and aluminum can form 1 additional covalent bond for a total of 4 bonds. When these elements have 4 bonds, they are not neutral, but instead carry a negative formal charge. We will discuss formal charge shortly. Group 3 elements like boron and aluminum are unique because of these properties, and we will see that this is a powerful source of reactivity that we will take advantage of later in the course. Moving over to group 4, we enter the group of carbon. As mentioned in an earlier example, because carbon has 4 valence electrons, it can achieve an octet by forming 4 covalent bonds. When carbon is in a stable, non-reactive state, we will always see that it will have 4 covalent bonds. By the way, this is also true for the element silicon, which is located directly below carbon. In group 5, we have nitrogen and phosphorus. Each have 5 valence electrons. When we place the 5 valence electrons around nitrogen, we start by placing 1 electron on each of the 4 sides. Notice that I haven't paired any electrons up yet, because I want to spread them out evenly around the atom first. After placing these first 4 electrons, there is 1 more electron remaining, so it has to be paired with one of the other electrons. It doesn't matter which I pair it with. After placing all 5 electrons in this way, we can see that nitrogen only has 3 unpaired electrons in the valence shell. How many bonds do you think nitrogen usually forms? That's right, 3. So our Lewis structure accurately predicts that nitrogen and phosphorus will form 3 bonds. It also predicts that nitrogen and phosphorus will have one non-bonding electron pair on the atom. Those non-bonding electron pairs, it turns out, are very significant to the reactions we see with both of these elements, so let's not forget about them. In group 6 we have oxygen and sulfur, each with 6 valence electrons. Placing their electrons evenly around the element symbols, we see that there are 2 unpaired electrons. This predicts that oxygen and sulfur each tend to form 2 bonds at those unpaired electrons. With 2 covalent bonds, these atoms will also have 2 non-bonding electron pairs in their valence shell. Finally, we have the halogens in group 7. With 7 valence electrons, we can see after placement that we only have 1 unpaired electron available for bonding. Therefore, we predict that halogens only tend to form 1 covalent bond, with 3 non-bonding electron pairs in their valence shell. This is similar to what we see with hydrogen atoms, by the way. Hydrogen only has 1 valence electron, and therefore only forms 1 covalent bond. Most modern periodic tables place hydrogen in its own group, in order to distinguish it from group 1, the alkali metals. In older periodic tables, hydrogen is sometimes seen in both group 1 and group 7, as a reminder that it can exhibit properties of both alkali metals and the group 7 nonmetals, depending upon the circumstances. Hydrogen is quite the versatile element indeed, which is great news considering it is the most abundant element in the universe. But I digress. Let's get back to the main topic at hand. Now that we know how many bonds various elements can form, I want to show you the different ways in which these bonds can be arranged. Let's call these different arrangements bonding patterns. These bonding patterns are extremely helpful when you are just starting out, as you can use them as building blocks or templates when you are trying to draw molecular structures. For hydrogen, the bonding pattern is quite simple, as only 2 electrons can fit in the 1s orbital around hydrogen. Because of this, only 1 covalent bond can form at hydrogen, and as a result, this is the only bonding pattern we see. For carbon, several bonding patterns are possible. Remember that in its stable form, carbon will always have 4 bonds. Those 4 bonds can be set up in the following ways. First, we can have 4 single bonds to other atoms. Next, we can have a double bond and 2 single bonds. In this bonding pattern, we have 2 single bonds connecting the carbon to 2 atoms. As we know, each of these single bonds consists of 2 shared electrons. The double bond connects carbon to a 3rd atom. This double bond involves the sharing of 4 electrons instead of 2. This makes sense, as each of the bonds still contains just 2 electrons. We will learn the specific details for how this occurs a bit later in the course. Another bonding pattern for carbon involves a triple bond and a single bond, each one connecting carbon to 2 atoms. This is still 4 bonds, of course, and therefore involves the sharing of 8 electrons in total. Finally, we can also have 2 double bonds, each one connecting the carbon to 2 other atoms. There are other bonding patterns we will see on occasion, but these involve carbon in more reactive unstable states. For now, these are the main patterns we will be focusing on. Nitrogen, as we saw previously, tends to have 3 bonds as a result of having 3 unpaired electrons in its valence shell. These 3 bonds can be observed in several different bonding patterns, as shown here. First, nitrogen's 3 bonds can be observed as 3 single bonds to other atoms. Because nitrogen has its non-bonding electron pair, and the 6 electrons in covalent bonds, there is an octet of electrons around the atom. Another way that the 3 bonds can be arranged around nitrogen is by having 1 double bond, 1 single bond, plus the non-bonding electron pair. Again, this gives us a total of 8 valence electrons, 6 of which are involved in covalent bonds. Finally, the 3 bonds around nitrogen can also be arranged in a triple bond, connecting nitrogen to one other atom. As in all of these bonding arrangements, notice that there is a non-bonding electron pair on the nitrogen atom. Oxygen forms 2 bonds when it is stable. This is due to it having an electron configuration with 2 unpaired electrons. In one bonding pattern, oxygen is observed to have its 2 bonds as single bonds to other atoms. In another bonding pattern, oxygen can have its 2 bonds arranged as a double bond to another atom. Notice that in both cases, oxygen has 2 non-bonding electron pairs in its valence shell. Finally, the halogens. Similar to hydrogen, the halogens are quite simple in terms of bonding patterns. As the halogens only usually form one bond, the only bonding arrangement is usually a single bond. This leaves the other 6 electrons arranged in non-bonding electron pairs in the valence shell. Here are just a few reminders and other tips you can use when starting out drawing Lewis structures. I won't go into detail on these, but I do suggest you keep them in mind when working on practice problems. For now, let's review the concept of formal charge. When chemical reactions happen, covalent bonds are broken, and new bonds are formed. During these processes, atoms can take on a positive or negative charge. We refer to the charges on specific atoms within a structure as formal charge. Formal charges can be present on just one or multiple atoms within a molecule. The total charge of a molecule is always equal to the sum of all formal charges on atoms within the structure. How do we determine the formal charge on an atom? The formal charge on an atom is the difference between the number of electrons an atom should have and the number of electrons it actually has. Therefore, if an atom has more electrons than it should have, it will have a negative formal charge due to excess electrons. If an atom has less electrons than it should have, it will have a positive formal charge due to electron deficiency. How many electrons should an atom have? The number of electrons an atom should have is equal to its group number. How do we determine how many electrons an atom actually has? We examine the structure. First, we add up any non-bonding electrons on the atom. Next, we look at the bonding electrons. We know that a bond contains 2 electrons, but because the bond is shared with another atom, we only consider 1 electron of that bond as being on the atom we are looking at for formal charge purposes. So each bond on an atom is worth 1 electron for formal charge purposes. Makes sense, right? As an example, let's consider the nitrogen atom in the ammonium ion, which has the formula NH4. As the structure shows, there are 4 single bonds between nitrogen and hydrogen in ammonium. Let's think about that nitrogen atom. How many electrons should nitrogen have? Nitrogen should have 5 valence electrons, as it is in group 5 on the periodic table. How many electrons does the nitrogen actually have? Let's take a look at that more carefully, so that we can distinguish between 2 different ways of counting electrons. In one way of counting, called counting for the octet, we can say that the nitrogen has an octet of electrons. That's because each covalent bond consists of 2 electrons. When calculating the formal charge, however, we count bonds in a different way. This method is called counting for formal charge. When counting for formal charge, we have to assume that only 1 electron from each bond is actually on nitrogen. That makes sense, of course, because a covalent bond shares the 2 electrons with each atom. What this means is that nitrogen really has only 4 electrons, not 8, at least where formal charge is concerned. Nitrogen should have 5, but actually has 4. So 5 minus 4 equals +1. So nitrogen has a +1 formal charge in ammonium. Since none of the other atoms in ammonium have a formal charge, the total formal charge of ammonium is +1, thanks to that nitrogen atom. As another example, let's take a look at this particular drawing, known as a resonance form for formaldehyde. Before we begin assigning formal charges, note that formaldehyde is a neutral molecule. Starting with the oxygen atom, we see that there are 6 non-bonding electrons, as well as a single bond. This gives a total of 7 electrons around oxygen. Oxygen should have 6 electrons, but it has 7. 6 minus 7 is -1. What does this mean? That's right. It means this oxygen has a -1 formal charge. Now let's look at that carbon atom. Carbon should have 4 electrons. There are 3 bonds. This means there are only 3 electrons on carbon in this structure, if we are counting for formal charges at least. So, anyway, what is the charge on this carbon atom? That's right, it is +1. That's because 4, how many it should have, minus 3, how many it actually has, is +1. Nice work. Okay, but why is formaldehyde neutral if it has atoms with formal charges? That's exactly right. The -1 charge on oxygen and the +1 charge on carbon sum to 0. You are doing awesome, by the way. Just a reminder regarding electron counting. The examples we just worked on together go over this in detail, but just to summarize, here are the 2 methods we use for counting electrons. First, remember that when counting for the octet, each bond counts as 2 electrons. For formal charge purposes, however, we split the 2 electrons of the bond evenly between the 2 atoms that are bonded together. So, for formal charge, each bond is worth 1 electron for each atom, even though we know there are 2 electrons in each bond. As we are going to see throughout the course, the chemical behavior of an organic substance is something that we are trying to predict based on what we know about a substance's structure. This is the key to organic chemistry. The structures we draw are our main tool for understanding how structure and reactivity are related. Because our structures are our main symbolic tool for communicating ideas in this language, it is absolutely essential to recognize the limitations of these symbols. Our drawings, our structures, do have limitations. Knowing limits, however, provides us with key insights on how to develop new tools for overcoming those limits. One crucial limitation of our structural drawings is that one single structure may not capture all the possibilities for where electrons are located within a molecule. Resonance structures are different versions of our drawings that show where electrons are located within a molecule. If we could draw all the possible resonance forms for a molecule, and somehow average all of those drawings into something we might call a resonance hybrid, it would be that resonance hybrid that could really show us how and where electrons were distributed. We could see regions around the molecule that were especially electron-rich, and other regions that were electron-poor. This would give us a really good picture for predicting the reactivity of that molecule. In this resonance form, for a molecule called nitromethane, we see a positive formal charge on the nitrogen atom, and a negative formal charge on one of the oxygen atoms. We can draw another resonance form for this molecule by moving the non-bonding electrons from the negatively charged oxygen. We can move these electrons down into a double bond, so that they are shared between the nitrogen and oxygen, instead of just sitting on oxygen. When we make this new bond to the nitrogen, we must simultaneously break one of the other bonds. Otherwise, there would be more than 8 electrons on the nitrogen atom. We can break the other double bond by taking those electrons and move them up to a non-bonding pair of electrons on that oxygen, which now has a negative formal charge, as it has gained an electron. Notice that when drawing resonance forms, we never break a single bond between 2 atoms, and we never move one atom to a new bond with another atom. The only changes we make involve converting the second or third bond of a double or triple bond into an electron pair, or turning an electron pair into a second or third bond. We also change the formal charges on atoms, but also notice that the overall charge on the entire structure stays constant. The true structure of nitromethane is a weighted average between these two forms, and other resonance forms as well. For example, the resonance structures we have drawn show that both oxygen atoms have a partial negative charge, rather than one being -1 and the other being neutral. Our resonance forms also hint that the true structure of nitromethane should have the same nitrogen-oxygen bond lengths, rather than one being shorter than the other, because of the presence of a separate double and single bond. In reality, this is true, as nitromethane is observed to have identical NO bond lengths. Additionally, these bonds are known to be a bit shorter than a standard single bond, but a bit longer than a pure double bond. This observation shows us that by using resonance structures, we can make more accurate predictions about the actual structures we are analyzing. When thinking about resonance, it is important to realize that a molecule does not interconvert between the different resonance forms, as it might in an equilibrium-type process. For this reason, we use a special double-headed arrow, as shown here, to separate resonance forms. When all the resonance structures are combined, we call the resulting structure a resonance hybrid. As an example, let's consider the molecule formaldehyde. When we draw the structure of formaldehyde, we do not immediately see how any of the structural features impart physical or chemical properties. One way we can get more information is by analyzing formaldehyde's resonance forms. Following the guidelines outlined on the previous example, I can draw a resonance form for formaldehyde by taking 2 electrons from this double bond and moving them to a non-bonding pair on oxygen, for example. It would be perfectly legal to put those electrons on the carbon instead. But I know that oxygen is more electronegative than carbon, so it is more likely that the electrons would go to the oxygen. The resulting resonance form we draw would now have formal charges present, with a negative charge on the oxygen and a positive charge on the carbon. What do these resonance forms tell us about the properties of formaldehyde? To answer that question, let's draw the structure of the resonance hybrid and look to that for some answers. The resonance hybrid would look like this. All of the atoms are connected by single bonds. The double bond between oxygen and carbon can be drawn as a dashed line, as a sort of average between having the bond present, as in resonance form A, and not having the bond present, as in resonance form B. Now that the bonds are drawn in the hybrid, let's include information about charges. Because we are averaging resonance form A, which has no formal charges, and resonance form B, which has a -1 charge on oxygen and a +1 charge on carbon, our hybrid shows partial charges on the carbon and oxygen atom. We can use the lowercase Greek symbol delta, with a plus or a minus symbol, to show these small partial charges and distinguish them from full charges. So what does this resonance hybrid tell us that the normal structure doesn't? Notice that we see a partial positive charge on carbon. That tells us formaldehyde should be reactive at that slightly positive carbon. Specifically, it should react there with negatively charged atoms, or atoms with a lot of electrons available. So does formaldehyde react this way? Yes. In fact, one of the key patterns of reactivity for formaldehyde and other aldehydes is that electron-rich atoms, like the oxygen in a water molecule, form new bonds specifically at that carbon atom. Additionally, when a new bond is formed at that carbon, the double bond breaks, and those electrons flow up to the more electronegative oxygen, which we also predicted in the resonance hybrid. You probably noticed that when I was drawing resonance forms, I used a curved arrow as a way to depict the electrons in a bond moving to an atom. These so-called electron flow arrows are actually a language and a tool that we use in organic chemistry. We will learn to use these curved arrows to show how chemical reactions proceed, how bonds are formed and broken, how protons are transferred from acids to bases, and how electrons can be distributed within a molecule. For now we will focus on using these electron flow arrows to keep track of electrons and bonding within resonance forms.